Our next speaker is Dr. Xin Ying, Lee Kuan Yew Research Fellow at Nanyang Technological University, Singapore. A proud Malaysian scientist making her mark on the global stage. Here's a striking fact for everyone. Since the 1950s, the world has produced over 8 billion tons of plastic, yet less than 10% has ever been recycled. And here in Malaysia, the problem is close to home. We are among the world's top 5 contributors to the ocean plastic pollution, with over 2 kilograms per person each year leaking into our seas. These staggering numbers also open the door to bold innovations, and that's where Xin Ying comes in. She is tackling plastic waste through breakthrough research in photocatalytic upcycling, transforming plastics into fuels and valuable chemicals under ambient conditions. For this, she received the Merdeka Award in 2023 and was named to MIT Technology Review's Innovators Under 35 Asia Pacific in 2024. Her work shows how science and sustainability can come together to drive a circular economy. Ladies and gentlemen, please welcome our very own Dr. Xin Ying.
Good afternoon, ladies and gentlemen. Thank you for giving me an opportunity to share my research, which is on the conversion of plastic waste into valuable chemicals at room temperature. Since 1950, there are more than 9.5 billion tons of plastics have been produced. However, only 9% recycled, 11% incinerated, and the remaining 80% have accumulated in the environment. According to the estimates from the United Nations, there will be more plastics than fish in the ocean by 2050. Currently, there are 2 existing technologies to recycle plastics, which are pyrolysis and mechanical recycling. For pyrolysis, it requires heating to 700 to 1000 degrees Celsius, which consume large amounts of energy, along with large emissions of greenhouse gases. And the products of the poisonous gas from the pyrolysis will harm the environment. And most importantly, those products from pyrolysis are mixed hydrocarbons with low value. For mechanical recycling, it can only handle certain types of plastics. Those conventional plastics, such as LDPE, which is the plastic bag, polystyrene, which is the styrofoam food container, these kind of conventional plastics cannot be recycled by mechanical recycling because they are soft and elastic, which will clog the machinery. And for PVC, they will actually release chlorine and also hydrochloric acid, which are corrosive to the machinery. And most importantly, recycled plastics have lower quality than virgin plastics. So because of this, there are many research efforts have been devoted to developing new technologies to recycle plastics. So this figure summarizes the representative literature work on plastics upcycling. As shown in figure A, they actually use ruthenium as the catalyst to convert plastic waste. And we know that ruthenium is actually a rare metal, which is expensive. Besides, they also require high temperature, 200 degrees Celsius, and high pressure, 0.3 megapascal, to transform the unwanted plastic waste into useful chemicals. For figure B, they used iron chloride as the catalyst, which is cheaper than ruthenium, but however, the product yields are low. So in total, they can only produce 23% of products. And for figure C, they used cheap ionic acid as the catalyst, but however, this research requires the use of benzene as the solvent. And we know that benzene is actually highly toxic and they are carcinogenic. So for figure D, this is the work published in Science. So they use platinum as the catalyst to transform the plastic waste. But we know that platinum is a rare metal. It is so expensive, and we have so much plastic waste, so it is impossible and it is not feasible for us to use platinum to recycle plastics. And for figure E, it is actually part of my previous work. So previously, we used a vanadium-based catalyst to recycle plastics. However, vanadium is also a metal-based catalyst, and it is highly toxic. So based on existing research works, most of the existing catalysts involve expensive metal, toxic metal, high temperature, and high pressure. So when I designed my new catalyst, I actually set 5 criteria. It must be non-metal, non-toxic, inexpensive, facile synthesis, and easy to scale up. Fortunately, after many attempts, I managed to develop a catalyst which is metal-free, and it can convert a wide range of plastic waste into useful chemicals at room temperature and atmospheric pressure. So in comparison to pyrolysis, which requires 700 to 1000 degrees Celsius, we actually managed to transform the plastic waste at room temperature and atmospheric pressure. So our catalysts actually serve as the chemical scissors to selectively cut the bonds in the polymers. So we can break down the polymers into small molecules, and these small molecules are highly usable in many different applications. And these are the 6 out of the 17 SDGs that we believe our work can contribute to. And by harnessing the carbon sources in the plastic waste, we actually view plastic waste as a resource, as a raw material for us to synthesize useful chemicals. So this is how we conduct the experiment. Firstly, we dissolve the plastics in an organic solvent. Then we add our catalyst into the reaction mixture, and we send the reaction mixture under light irradiation with the presence of oxygen. So basically, we need only plastics, oxygen, light, and catalyst in order to form these high-value chemicals. Traditionally, it requires 100 to 1,000 years for non-biodegradable plastics to decompose. With our technology, we can shorten the process to 1 day. We need only 1 day to transform the unwanted plastic waste into useful chemicals. I'm sure that everyone knows that hydrogen is a clean energy, a clean fuel. But the problem associated with hydrogen is that it is highly flammable and highly explosive. So the transportation and the storage of hydrogen are challenging because it is so flammable, so explosive. So what we do is that we actually store hydrogen in liquid form. 1 liter of formic acid can store 570 liters of hydrogen. And we can produce this formic acid from plastic waste. Other than benzoic acid, we also produce acetic acid and acetone phenol. So these are actually highly valuable chemicals because they can serve as food additives, antiseptics, food preservatives, as well as fragrance. They are integral to our daily lives. And just now I mentioned that recycled plastics have lower value compared to virgin plastics. Instead of producing recycled plastics, we actually break the polymers back to their monomers, such as terephthalic acid and ethylene glycol, and these monomers can be used to synthesize high-quality virgin plastics. So what we do is that we actually view this as a plastic upcycling technology instead of plastic recycling technology because we add values to the products. And in our opinion, we actually harness these carbon sources from the plastic waste. So this plastic waste actually is a resource, it's valuable raw materials to us for us to synthesize these high-value chemicals. So this summarizes the recent advances of our work. So basically, we can upcycle plastics covering racing code 1 to 7. So racing code number 1, PET, is those mineral water bottle. HDPE is the detergent bottle. PVC pipes. LDPE is those plastic bags. PP is the transparent food container. PS is styrofoam packaging materials and styrofoam food container. PVAC glue, and EVA shoe sole. So basically, we can upcycle the plastics from racing code 1 to 7. And just now I mentioned that mechanical recycling can only handle clean and sorted plastics. So we want to compare whether our technology is better than mechanical recycling or not. So what we do is that we recover the styrofoam food container from the dustbins of NTU, and we actually send it for experiments, and we realize that the product used from the contaminated styrofoam are actually similar to the clean styrofoam. So it suggests that our technology can also handle those contaminated plastic waste. And just now I also mentioned that for mechanical recycling, it requires the sorting of plastics because PVC will release hydrochloric acid and chlorine, which will poison the machineries and also poison the catalyst. So what we do is that we purposely add some PVC into the plastic waste stream. So for PVC, this is for figure A, that's the product used from the single element PVC. For figure B are the product used from PP, and figure C are the product used from single element polystyrene. And summation means that we do the mathematics by adding these three together. And for figure E, mixed plastics means that we set up an experiment by mixing these three plastics together. And we realize that the yields from the mixed plastics are actually similar to the summation. And in fact, the yield of acetic acid is even higher than the summation. So it suggests that our technology can upcycle a wide range of plastics and mixed plastics, and to the best of our knowledge, this is actually the first work that can upcycle such a wide range of plastics as well as the mixed plastics. After that, we actually expand our work to biomass depolymerization. So other than plastic waste, biomass waste is another global waste that surrounds us every day. So we actually try to depolymerize the lignin structure. So after 24 hours of light irradiation, the lignin turned from dark brown color to colorless. And when we send some sample to NMR analysis, and we realized that we produce benzene, toluene, and phenylene. So for benzene and toluene, they are widely used in many different industries as a solvent, and phenylene can serve as a raw material and also a precursor for the synthesis of Parkinson's drugs. We further expand our research by depolymerizing nitrile gloves. So we cut the nitrile gloves into small pieces, and as we can see, okay, so these are the nitrile gloves. And after 24 hours of light irradiation, those nitrile gloves disappear. By the way, this yellow color is our catalyst. Our catalyst is in yellow color. And without catalyst, a control experiment, after 24 hours of reaction, these nitrile gloves broken into smaller fragments, but they cannot be converted. And with the presence of our catalyst, we can produce levulinic acid and formic acid from nitrile gloves, and these are high-value chemicals. And this is a collaboration with a hospital. So these thermoplastic shells are widely used by head and neck cancer patients during radiation. So this hospital that contacted us, they asked us whether we can do something about it because they have about 1,000 units of these thermoplastic shells to dispose every year. So it is actually quite large and quite bulky. So we conduct the experiment using the same catalyst and also same technology. So we realized that we can convert these thermoplastic shells into nano fragments which cannot be seen by naked eyes. So we also have control experiments. So for this one, if without catalyst, without light, and this one is with the presence of light but without catalyst. So in comparison to the control experiments, with the presence of both light and catalyst, we can break down the thermoplastic shells into small molecules. And lastly, I would like to thank NTU, National Research Foundation of Singapore, as well as Malaysia, Merdeka Award Grant, founded by Petronas and Shell, for supporting my research. And I'm also very grateful to MIT Technology Review for recognizing our work. And these are the 6 out of the 17 SDGs that we believe our project can contribute to. As a Malaysian, I'm a Malaysian, I hope that this technology can be implemented in Malaysia and other Southeast Asian countries so that we can create a cleaner, more environmental friendly, more sustainable environment for our future generations. Thank you.